yeah, also like people have said, I don't really mind that much if I don't get through all my slides. I have more than I need. So maybe mostly this is just introduction to sofic entropy, and maybe I don't get to say anything about other more recent stuff. That's okay. Just ask questions if you want. But, oh no, okay. Everybody else has done this. I haven't gotten used to it. Okay, cool. So yeah, so I want to start with a kind of problem that has come up in a few other talks already, which is taking something like a random labeling, a bi-infinite labeling, you can think of it as a Z or something, and apply some special kind of map to it to generate another random labeling. Okay, so an important constraint is that I want to do this in an equivariant way, which means, okay, so I want to really restrict to a pretty simple example of this, specifically where this big phi up here, that's like the factor map. So it's sending this labeling to that labeling. And specifically how it's doing it is that there's this map little phi, where if I want to know the labeling on this block, I just have to look at like the 5 blocks directly above it. Okay, so specifically that's a block, what I can call a block factor map. Yeah, in general, maybe you would just want this to be like measurable, but it should have this property that specifically if I shift this input sequence by some amount, it shifts the output by exactly the same amount. Okay, and you can see this way of generating it does that. And maybe one nice thing about that is that I don't even have to think about like where 0 is in order for this map to be well defined. So maybe that's a nice thing. Okay, yeah. So the block factor maps will just make pictures that are easier to see. So let's just pretend that's true. Okay. Okay, so Yunan already talked about, I think on Tuesday, maybe the first thing could be some easing model at some temperature, and maybe you want to generate an easing model at some other temperature. So that's a nice question to ask. I think Ahmed maybe in his talk mentioned another similar kind of situation where maybe this lower thing is a distribution that you care about for some reason. Maybe it's concentrated on like solutions to a problem that you want to solve. And maybe you want to generate it by something that's really easy to generate. So like if these are just IID labelings, and you can generate something which has more interesting properties, that would be really nice because you can just do it in this nice finite way. Okay, so in that case, you called this bottom one a factor of IID. Okay, but to go back to an even more simple problem, let's assume that these are both IID. And what I'm trying to do is say this is just 2 colors, red and blue. And I want to generate an IID sequence of 4 different colors in this particular way. I want to see if that's possible to do that. Does that make sense? Yeah. So if I didn't care about equivariance, what I could do is just sort of group them into pairs of 2. And that's kind of equivalent to having 4 symbols, but that you can do that if you fix a point that's the origin, but then that changing the origin changes that. Okay. So trying to do it in an equivariant way is a little less clear to see if that's possible, I think. I don't know why it's 7 again. Okay. Those are just the same setup repeated. So the idea maybe is that this bottom labeling is like more random or something, and you shouldn't be able to do that. Or another way of putting it is that it contains more information. So that's relying on thinking of these as maybe some kind of coding problem where this is like a sequence with some information that you're trying to encode by using smaller amount of symbols. And you can't. That makes sense that you shouldn't be able to do that. Okay, so I'll come back to that problem. That's what it's supposed to motivate. Trying to talk about information a little more specifically. What exactly do I mean by information? And I want to do an introduction to standard entropy, which I say maybe it's not like the most standard thing. It's not completely non-standard either. But yeah, this will generalize much better to what sofic entropy is, at least. That's the goal. Okay, so specific fixing a finite set A. So in those examples, this was like the colors that you're going to label things by, which is a finite set of symbols. Probably also call it an alphabet at some point. And I have some measure on that alphabet. And what I want to count is how many finite strings of length n in that alphabet have like statistics that are given by nu. And by that I mean, so I don't really care about the order of the symbols just yet. I just want to know like the number of times I use symbol A or the proportion of times I use symbol A is equal to mu of A. Okay, so that's simple version. There's just a little problem with like, okay, this is going to be a rational number of denominator n, so that's not something that I want to have to require. So actually instead, it's this slightly more complicated thing saying basically the same thing, where I allow just a little bit epsilon error. So now for any mu, at least as long as n is big enough, I should be able to have at least some labelings that give me the right statistics, that I use all the symbols the correct proportion of times. And I want to call these epsilon typical strings of like 10. Yes. Okay. Okay, so ordering doesn't matter just yet. Well, okay, so ordering doesn't affect the statistics, but different orderings are different strings, right? Okay, so this is the same set I just had there. And what I want to do is just count how many of these strings there are for n. So maybe it's not too hard to convince yourself that it should sort of grow exponentially in n. You can think about that at some point if you want. But there is like a nice, well-defined exponential growth rate here. And I'm going to define that to be the entropy. Okay, so another comment. Decided not to put this in the slide, but I can mention that. So Russ mentioned yesterday this Paquette's lemma. You can show this limit exists using that kind of subadditivity thing or superadditivity, whatever. Yeah. Okay, so it's an exponential growth rate of the number of typical strings, and then you have to set epsilon 0 to make sure you're actually counting things that are truly close to mu, not just approximately. Okay, gonna see some more strings of limits like this in the future, but this is a nice first example, I think. Okay, so you can calculate this by just doing some kind of combinatoric stuff and using Stirling's approximation and so on, and you get exactly this formula for Shannon entropy that probably everybody has seen before. Okay. So yeah, other ways of introducing Shannon entropy is just to write down this formula. Yeah, that would have been faster, but yeah. So yeah, no, I just want to say a few non-rigorous things about why you would think about this as an entropy, I guess, if you're thinking about this formula. Right, so if you have more strings that have the correct statistics, that kind of means that mu is imposing less restriction on the strings that you're allowed to send or something like that. So at one extreme, like if mu is completely deterministic, you can only send one signal essentially at any length. So it doesn't let you transmit information. So that sort of corresponds to having entropy 0. I'll do some more calculations in the future, but yeah, that's supposed to be maybe some idea of why you would think about this as a measure of randomness, I guess, or information. Okay, so it's a few just examples of calculating these things in case you haven't seen it before, haven't seen it recently. If you just take the uniform measure on A, so A is a finite set, okay, every single point gets this measure, and then it's pretty quick to get that the entropy is log of the size of the set. Okay, so that intuitively maybe should be the most random thing. You just choose something uniformly random from a finite set, and you can show that that's actually true by like a convexity stuff. Okay, so this is the most random thing, has this much randomness, and everything else has strictly less. And then this is just the calculation of what I said intuitively a minute ago, is that if you have just a measure that puts everything on one symbol, that's the only symbol you're allowed to use, then you get 0 entropy. With the caveat that I just have to say that 0 log 0 is 0, which is hopefully not too controversial. Okay, and there's plenty of other properties. Maybe you've seen some of them before, but instead of just giving a big list now, I'll just mention them when they come up, if that's okay. But any questions? Okay, so what I want to do now, I'll come back to the counting interpretation. Like I said, I think that's good for motivating what sofic entropy is about. But for now, when I'm talking about the rest of classical entropy theory, I think I just want to kind of black box Shannon entropy as a measure of randomness or information. Okay, so let's do that for a few slides. Okay, so now I have the same thing that I had before. I just have a random labeling by infinite of, say, red and blue colors or anything else from like a finite alphabet. Assumption I'm going to need to make at some point, I'm just going to start now, is that this is a shift invariant labeling. I'm not exactly sure how natural that is for like a coding theory perspective, but if you're thinking about mu as like, say, a using model or something statistical physics related, basically what I'm saying is that it's spatially homogeneous statistically, right? So it doesn't have to be supported on individual states that are shift invariant because there's only 2 of those, but the law does have to be invariant, which I think is pretty natural assumption in that environment. Okay, so what I want to do is say how random is this labeling, this infinite labeling. So if I just like take mu as a measure on some set and I try to calculate its Shannon entropy, unless I've picked one of those stupid things where it's just on like all red, all blue, or some mixture of the two, I'm going to get infinite Shannon entropy, which maybe is also not too surprising. It's an infinite system, like it should contain an infinite amount of information, and except in trivial cases. So that's probably actually good that that's what happens. But that's not what we want to do. We want to actually get some non-trivial thing here about information here. So we should do, also from the perspective of this being an infinite string with an infinite amount of information, maybe it makes more sense to say how much information is there per symbol in the sequence. Okay, and let's see how we can do that. Okay, so this is called the Kolmogorov-Sinai entropy rate. And yeah, this all this stuff so far is kind of from the 40s and 50s, basically. Okay, right, so same setup here. I just have some shift invariant law, but I random labeling X, just a little more concisely. What I can do is just look at some finite string of symbols. Okay, so I still don't have an origin marked, but I'm imagining I'm looking at a marginal on, say, minus n to n. And okay, I noticed after I made these slides that this is an even number of blocks. So I don't think that's a problem, but yeah, technically this doesn't fit that. But this is the point. So it actually doesn't really matter that much. I just want to look at some finite length of symbols here. And if I generate, say, random labeling X, I can then just restrict it to these this block, and I have a random finite thing. And for that, that's just a measure on a finite alphabet, which is ordered strings of symbols of length 2n plus 1. So that has a Shannon entropy. So what I can do is then just look at that Shannon entropy of this restricted thing. So if I just take n to infinity, I'm going to get exactly what I had before. I'm going to get infinity. But what I want, right, is entropy per symbol. So I just take that divided by the number of symbols, and then take the limit that then goes to infinity. And that, again, that converges by this sub-super-additivity. So, okay. And that we can call the Kolmogorov-Sinai entropy rate of mu. Okay. Good. So back to doing a few examples. If I take some kappa on just the alphabet, probability measure on the alphabet, and then I just label every symbol in my bi-infinite sequence independently using kappa, that's called a Bernoulli shift, or IID labeling, whatever you want to call it, based on your native language, I guess. Yeah, ergodic theory, I'll probably keep saying Bernoulli shift, but it's just IID labelings. So that actually is pretty easy to calculate the entropy rate from this definition. So if you generate these IID labels on a whole bi-infinite sequence, if I then restrict to just a finite string, I just have an IID on that finite window. And here's where I'm bringing in one of these other properties of Shannon entropy. I said I'd mention a few more. If I take a Shannon entropy of a product measure, it's the same as just adding up the individual entropies of the separate symbols, which I think is also a natural information theory kind of thing. So if I have these 2n plus 1 symbols, neither of them interact with each other. Each one of them has a certain amount of information. The total information is just the sum of the separate things. Okay, so then from that, you can get pretty quickly that the entropy per symbol is like what it should be, just the entropy of every individual symbol. Yeah. So this is something I want to fix on, and this is like something that should be true of any reasonable entropy rate that you would want to define. If you have a Bernoulli shift or an IID, the entropy per symbol should be an entropy of an individual symbol, right? Okay, so that's something that, okay, and you have to calculate once you make a definition. In this case, it's pretty easy, but I think that's something that's reasonable to get pretty attached to as a property of an entropy rate. Okay, but the entropy of a newly shift is Shannon entropy of a base. So the way to say that, write it on the board 100 times. Okay, so here's another nice property of this KS entropy rate, the Kolmogorov-Sinai entropy rate, just on a Z system. Meg, go ahead and say that you should not get too attached to this one, but it's good to introduce just as an introductory talk kind of thing. So here I'm back to this picture kind of from the second slide. I have this other system. We've been looking at this picture for a little bit, and I want to go back to the question of, can I use it to generate this other like more complicated system? And the setting again was that I want to see if it's a factor of mu. And again, pretending all factors are block factors. Okay, so when I'm proving this theorem, I'm just going to think about block factors. I think that contains the nice idea that's worth showing in 45 minutes. Okay, so this is exactly what the intuition that I suggested on the second slide, I think, is that if something is generated by something else, it shouldn't have more information per symbol. So the entropy rate should be at most the other one. Okay, so let's see the idea of the proof here. Okay, so I'll call this this random labeling X, and that's the random labeling Y with the corresponding laws. And again, I'm going to bring in a property of Shannon entropy here. But if I look at this, so this is what I'm trying to calculate the entropy or bound the entropy rate of this one in terms of that one. So imagine I'm trying to see what the entropy is in this block on the lower system. So I think it's random labeling Y and say like what's going on in this block. Well, it's a function of all this stuff, right? So if I want to know this symbol, I need to know these 5. If I want to know that symbol, I need to know these 5 and so on. But if I want to know all these symbols, I need to know the symbols up above on just like a slightly wider range is the point. Okay, so it's not exactly a function of the same symbols, but since I'm assuming I have a block coding here, I just pick up like an extra sort of coding radius. Okay, does that picture make sense? Okay, so then here's kind of the calculation you do. So here's just the formula for the entropy rate of nu. And this inequality is what you get from this property of Shannon entropy, a new property of Shannon entropy that I'm bringing up now, is that if some like finite random variable is a function of another one, then it can't have more Shannon entropy. Okay, so that's what's going on here. But then I just pick up this extra plus R in every direction. And that really doesn't matter in the limit. And the point is that I'm picking up stuff that's from the boundary. And since I'm on just the integer line, like as n goes to infinity, that becomes negligible compared to what's on the inside, okay, which is an idea that's come up some recently. Yeah.
So that was given actual proof that you see as like block that negative integer, right?
It does give that.
Well, if we restrict to that case, like of continuous factors, but isn't this literally done? Like inequality
continuous. Which inequality?
So
this one here.
Like this, like if B actually only depends on like R, like it has an actual coding radius.
Oh,
That's fixed, right?
Yeah.
So this like actually works
in this case, yeah.
So yeah, is the actual proof like by approximating by this, or is it like a little bit more?
I think you can prove it by approximating by this. Yeah. But these are sort of these block maps are like dense and whatever you want by like a stone virus cross or something. You agree with that? Yeah. Yeah, this, right. Yeah, there's a few more stuff like that that you can find in a lot of books at this point. Yeah, so this is still like the kind of old stuff. Yeah. But yeah, I think that's the main idea of if you have a factor map, you can use it to bound entropy by generating stuff like this. Okay. maybe this is a strange order of putting things. Yeah, I guess first, like I mentioned, I've been drawing pictures in Z, but the same kind of thing works in Z2 or any other amenable group. Because again, the point was that you just pick up this boundary stuff. And it's kind of exactly what it means to be amenable, is that you don't have too much boundary compared to interior when you're taking this kind of limit. Right. So the right definition of a fullness or of an amenable group, for example, V2, is you just take the exact same kind of limit, but you pick like rectangles in ZD or a fullness sequence in an amenable group, and it's okay. And what you can actually get out of this monotonicity thing from the last slide is that, okay, so the definition here, a pretty natural one, is that you have an isomorphism between two shift invariant measures. If there's a factor map, which is actually invertible, the inverse is also a factor map, you can ignore null sets. So like one can generate the other in an invertible way, specifically. Okay. And since these factor maps the factor map and its inverse are both non-increasing, that tells you this entropy rate is actually isomorphism invariant. Right. Okay, so these Bernoulli shift example we're looking at, we're like, can the 2 shift generate a 4 shift? The answer is no. And that's coming from a rigorous version of this intuitive idea that like there's just too much information per site, and you can't get over that with a factor map. Okay. And yeah, any 2 Bernoulli shifts with different base entrophies have to be non-isomorphic more generally. So that was the big result for Kolmogorov-Sinai entropy in like the late 50s, that people didn't know how to solve this before entropy rate was introduced. Okay, I think that's the last thing to say about this sort of classical set. The last thing I have to say about it for now, anyway. Okay, so obviously the next thing to do is try to do this on a tree. So what you could do, and there's also sort of an obvious definition you could take, like I was mentioning, fullness sequences and boundaries, I guess, and maybe you already know this is not going to work. But there's sort of a natural thing to try to do, is that maybe you could say, well, the only important thing is that I had some kind of finite exhaustion. Like I just wanted to look at finite versions of my system and then take their Shannon entropies and then take the limit. So this is like kind of the natural thing to try to do, I think, right? Just look at large balls in the tree and take that limit and hope it exists and see if it works. Yeah, so this is just wrong, unfortunately, for any reason that I think you would want. Anything you would want out of it, it's not super good, I don't think. Well, anything I want out of it. So it's not isomorphism invariant. Probably some people could say that that's maybe not important if you just care about a single system, not up to isomorphism, but the exact system. But that's not good for this sort of like original application of distinguishing Bernoulli shifts. You really want an isomorphism invariant for that. Okay. So this is a problem for a lot of people. So we'll talk more about that in a sec. It can increase under factor maps. That's not good, but as I mentioned before, it's something that maybe we're just gonna have to deal with. And this, we'll see if I get to talk about it later or not, but it also fails to do some things that entropy should do in statistical physics kind of settings. Okay, so this may be too much on a slide, but okay, so I want to talk about why it's not isomorphism invariant. What I have here is two systems that are the same. Okay, so I'm looking at a free group, and just like with the line, I'm just labeling all the elements by red and blue. And I've taken just some random labeling here of red and blue symbols on the vertices of this tree. And on the right, all I'm doing is just taking the exact same labeling, but at each vertex, I also record what was at its neighbors. Right, so there's no more information here. There's actually the exact same information in both pictures. This one's just kind of duplicating things over and over again. But correspondence between these makes sense. Yeah, so it's a lot to look at, but there's really not that much going on. Yeah. So these are isomorphic, right? So this you can generate by just, there's this map that just sends this to its neighborhood labeling, and then that's invertible by just dropping all the extra information. Okay, so they should have the same entropy by like a good definition. But if you look at like how much information is contained in a ball as measured by Shannon entropy, if you take the same ball, just take one ball over here and take how much information is in there, it actually has the information of the ball plus its boundary, because I have all this boundary stuff. And that doesn't go away as you try to take this normalized volume limit because trees, non-amenable groups have non-negligible boundaries. Okay, so if you take this kind of naive way of defining entropy per site as like just doing this kind of spatial average over balls, you get something that's not isomorphism invariant. Okay, so this is actually strictly bigger, and by doing like bigger and bigger, like kind of neighborhood labelings, I guess, you can get something that like goes all the way to infinity, right? So there's really no control over the entropy. Yeah, I think there's a natural way that I think Peter Byrne has looked into of like turning this into an invariant, but it's always going to be 0 or infinity. Okay, so you can get an invariant out of this, but it's not very refined, I guess. Okay, so that's not a good definition for that reason. That's something we'll be able to solve with specific entropy. Okay, so I guess I'll have to draw a little bit of a picture here that I decided not to put into a slide because I was lazy. There's a nice example from the 80s of why even if you're not attached to this like naive definition, if you're just want to say my entropy per site should be equal to the base entropy for Bernoulli shifts, like even then you have to drop this idea that factors can't increase entropy. Okay, so here's what you can do. You just take your tree. Okay, so maybe you label it by zeros and ones. We'll do that. Pretend this is random. Okay, so let's just say that's an IID labeling of all the vertices by ones and zeros. You can put a labeling on the edges by ones and zeros by just putting a, let's just say there's a 1 if they're different and a 0 otherwise. Yeah, and so on. Okay, so I have this labeling of the edges, and then what I'll do is just sort of associate, maybe do a few more. That's different, the same, different, okay. So I'll take, at each vertex, I'll associate it with the pair of labelings that's like, what was the edge up and what was the edge right? So this one is going to get like 0, 1, it's going to get like 1, 1, 1, 0, 0, 1, and so on. So just to make sure I have a nice, I want a nice vertex labeling again, is all I'm doing here. But if you think about it, like these are IID labelings of the vertices now by pairs of symbols like 0, 0, 0, 1, 1, 0, 0, 0, right? Because whether I change over and different edges are independent choices. So this means that the Bernoulli 2-shift, the uniform IID, actually can generate in an equivariant way the 4-shift IID. So you can somehow get more information per symbol under a factor map. Okay, and that's something that's, yeah, when this was introduced by Ornstein and Weiss, okay, I wasn't around then, but it's probably pretty demoralizing that like maybe there's not going to be an entropy theory that you want for free groups. Okay. Okay, yeah, and also what it tells you is that if you are going to try to define an invariant to replace the KS entropy rate, and you want to prove its isomorphism invariant, you're not going to have the same proof as before, I guess. That's just a smaller comment, but. Okay, I have 15 minutes, right? So one way of looking at this problem is that these radius n balls that I was trying to average over in this like naive definition of entropy rate, they don't locally converge to F2 in this Benjamini-Schramm sense that we've seen a few times this week. So if you just fix some radius r and take n really big, you can still kind of see the edge in a non-trivial, like a non-negligible fraction of these radius r balls, right? So you choose a random v in the ball, like it might actually be close to the edge. So one thing, if you think that's a problem, what you might do is just use a different sequence of graphs that do converge locally to F2. And as we've seen many times this week, you just take like a random 4 regular graph, it converges locally to F2. Okay. So that may seem like a good idea then, I guess. You can fix this problem by just taking some other graph sequence. Okay, here's a commuter diagram, sort of. So this is, I just want to indicate why that doesn't quite solve all of our problems by having a schematic picture of like what was going on in, say, Z2. Okay, so this is what I suggested on the last slide, that maybe this is what we want. Maybe we want like some finite model, like we want to have something that's locally like Z2. And the way we were doing that in the immutable case was just by passing to a marginal on a large box. And so you can think of that as a finite system that's locally like this infinite system, right? So both in terms of the graph structure and in terms of like, do we actually have some random labeling on this block that's like supposed to be a finite version of the infinite labeling, right? And we have this nice way of doing that by just taking a marginal. And now once we're in the finite world, we can like take the Shannon entropy, we can normalize it, and then take a limit back up to the infinite world, and we get a nice entropy rate. Okay, so far, the only big idea here we have is that maybe there's a better thing to put down here. But once we're looking at this like external graph sequence, okay, that's a great idea, but now what do we do? Like we don't have a marginal map. We don't have a way of saying what is a finite model from mu on this like random regular graph. Okay, so that's what we need to solve then. So actually what we're gonna do is there's a map that goes the other way. So if you have, say, something that's on a finite graph, G, that looks locally like F2, you can use it to produce an infinite system and then compare that to this system and try to make that work. Okay, here's a nice, great random regular graph here. And it's, as we talked about, it's locally like F2, at least if there's enough vertices. And I'm adding on some structure here, which maybe not everyone has this week. What I've actually done is I've drawn two, let's see, a few people actually use the permutation model already. So that's what I'm doing here. I'm drawing two uniformly random permutations of the vertex set, the red permutation and a blue permutation. And I'm also not forgetting like which was red, which was blue, and which direction everything is going. And that's a nice thing to do because that lets you match things up with the Cayley graph of F2 in like a unique way. So like if I have a ball, actually let's do this, yeah. So I pick a random vertex V here. I don't know how visible that is, sorry. I can do this. Maybe that helps. Right, so not only is it locally tree-like, but like I can exactly match this up in a unique way with the corresponding radius ball in F2. Right, I can say that F2 has a blue generator and a red generator, and there's a unique a way of lifting this over there. Okay, so that extra data is helpful. Because if I take this random labeling of this finite graph, I can then lift that random labeling specifically in a unique way. And that gives me a random labeling of the radius 2 ball in F2. And what I want to do then is that random labeling, if that's close to the marginal of mu on F2, I want to say this is like a good model for mu. Or maybe more in terms of like what I was saying with Shannon entropy, this mu has like, or this X has local statistics that are sort of determined by mu, at least out to like radius 2. Yeah. And now we're taking into account like some sort of geometry here too, right? I'm not just counting the labelings on the sites and whether those occur with the right frequency. I want to look at like labelings of neighborhoods in a graph and make sure those occur with the right frequency and so on. Right. So mu is imposing a constraint on labelings of these graphs. The picture. Okay, and then what I do is I just take those to be my analogs of these epsilon typical strings in the introduction to Shannon entropy from before. And now I can say like I have R epsilon typical labelings. If when I look at these like R neighborhood empirical distributions, those are close to the R neighborhood marginal of mu. So their statistics on radius R balls are basically what mu says they should be. On average across the graph. Right. Okay, so these X's for now are like deterministic labelings, and the randomness I'm getting is by choosing a random vertex and looking at what I see. So I can call these good models for mu, and then I take basically the same limit from before. I'm just counting how many of these there are over a particular graph sequence converging to F2. So right here, I'm thinking of this as being a deterministic sequence of graphs. you could just sample a sequence of 4 regular graphs, or I guess, yeah, 4 regular graphs uniformly, take one fixed realization of that, and it's going to be converging to F2 with probability 1. And you can use that to define this kind of quantity here. So any such sequence of graphs that have this like nice labeling structure, I can call that a sofic approximation. That's F2. Okay. There's a more general definition for that too, but just I think this captures a lot of the idea. Okay, and then so that's a fixed particular sequence of graphs. I can say, what is this sofic entropy? And I denote it this way. Okay. And I also want to highlight here that this sigma, so it's not like the KS in a way, like it's not just some notation that's saying this is sofic entropy. This is a particular sofic approximation to the group, right? And it's still unknown like how much it really depends on that sofic approximation. Is an interesting problem. It's known that there are some mu, like even on F2, where this can be either minus infinity for some sigma, which means you don't have any labelings that match the statistics, but for which there are other sigma where you have some positive number here. But it's not known whether they're 2 different positive numbers. So effectively, if you take 2 different like large graphs that are like F2, they either have no labelings that have the statistics specified by mu, or they have like, or maybe one of them has no statistics, no labelings, but the only other option is they have basically the same number up to like sub-exponential factors in the size. Okay. Questions on that? Yeah. Sure. Mm-hmm. Oh yeah, that's a good thing to say here. Thanks. I meant to say that. So if there is a sofic approximation, the group is called sofic. So this is F2 is a sofic group because, yeah, you can generate random regular graphs that approximate it. Like I said, I've been a little bit more restrictive with the definition of what a sofic approximation is than I should be. And if you drop some extra condition I have here, that maybe it would be hard to explain what it is in the context I've set up so far. It's unknown whether there are non-sofic groups. So there are specific groups that might not be sofic, but it's unknown whether. Yeah. I think the answer is that it's not known whether that can make a difference, and except for this issue with like maybe the limit is minus infinity while the lim sup is positive, and stuff like that. Lewis sometimes takes an ultra limit there, but yeah. But yeah, here you can't do like a Ficetta lemma thing to get an actual limit, actually. Yeah, so you have to do some kind of business here. Yeah. Okay. 5 minutes. Right? Okay, so yeah, we want to verify these kind of nice properties that entropy rates should have. So the first one is that if I have an IID labeling, or what I've also been calling a Bernoulli shift, like I said, it really needs to have this per site entropy that it obviously should be. Like that's something that the definition like needs to satisfy. Okay, and this is like not really that close to a complete proof, but the upper bound is actually exactly the counting argument that I showed at the beginning of the talk about Shannon entropy. So you can get an upper bound for the number of like actual good models for this Bernoulli shift by just saying, well, their single site statistics have to be kappa. And like there's this many things that you're labeling by the elements of the alphabet. So like there's at most this many things that have the correct single site statistics. Well, okay, sorry, there's exactly this many up to sub-exponential things that have the right single site statistics. So as an upper bound for the number that have the right neighborhood statistics. Okay, but you also want to know that this lower bound, and half of the argument, I guess, is that if you just pick a random labeling of the the finite graph by just like putting ID labels on the vertices with log kappa, then without even using like fancy modern concentration stuff, you can just get that that's like with high probability actually going to be a good model in the sense of these neighborhood statistics, right? So you don't just want like the right frequency of labelings. You want to know that like there's statistical independence also between like neighbors, right? So it seems a priori like it's a stronger requirement, but you do end up getting the same number of things. Okay, so again, this is only like half the proof of the lower bound, but that's the half that's easier to just put up on the slide. And the other thing which I'm going to be able to give you even less of an impression of is like, why is this actually isomorphism invariant? Okay, so here's one idea for one way to prove it. So if you actually have, so these two systems, mu and nu, and suppose that mu can generate nu in like an invertible equivariant way. So let's fix one of these isomorphisms, phi. And okay, so there's some way of using phi to send good models for mu to good models for nu. Okay, so you can't like literally just apply phi, I guess it's a little more complicated than that, but you can do like what I think it's intuitive that you should be able to do, right? So in the infinite setting, this can generate that. It's intuitive, like you should be able to probably do the same thing in the finite setting. If you have something that looks like a good model for mu, you should be able to generate something that looks like a good model for nu. Okay, and then what you get if you pair these together is a good model for something that's called the graphical joining over this is not phi of the pair. And the trick is to show that first X has the same entropy as this graphical joining, and then kind of by symmetry, so does Y. Okay, so if you take this X and use it to generate a good model down here, so it's something that X has the same statistics as mu, Y has statistics specified by nu, and then there's also like a correspondence between them that's sort of specified by phi. Okay, so obviously this like, you can go back the other way. This is like an injective map, right? So the number of good models here is at most the number of good models here. But you can argue that it's like almost invertible in the other direction. That if you start with some pair of good labelings here and then just drop Y, and then like generate some Y prime using this method up here, you get something that doesn't have to be exactly Y, but it has to be like pretty close. And then there's like not too many things up the sub-exponential factors that are like close to Y. Okay, and you get it that, yeah, the exponential growth rate of these things are the same. Okay, so this, I guess you can get across at least that there's a way of doing this that's like pretty different from you can't just use a monotonicity, but that's doable. Okay, I think, yeah, just maybe the last slide I'll do here. So yeah, this gives you that Bernoulli shifts with different base entropies are not isomorphic with the free group. So until Lewis's work on this was like unknown for a pretty long time. So there was this Ornstein-Weiss example where you can generate more entropy, but it was a non-invertible map, right? So if you just keep track of where the changes happened, you forget like a parity, like you lose like one bit of information. So it's unclear, like, yeah, how much of an obstruction that really was. But yeah, so Bernoulli shifts on a tree example or any other sofic group, if they have different entropies, they're not isomorphic. Yeah, and that wasn't even known for like the two and three shifts before. Okay, so that's the end of the actual talk. So that's how it worked out for that part. Okay, so if anyone wants to talk about spin system stuff like afterwards, I'd be very happy to. But yeah, all right, thanks. Yeah.
So there's also the
for the isomorphism problem.
Yeah, for the
yeah, so the converse is it's true for an arbitrary countable group even, which is the last bit of that was done by Brandon Seward just a few years ago. But let's see. I'm not super up on the history of that. I think maybe, Lewis, did you do the sofic case?
Yeah.
Okay.
Yeah. There's an argument through the second.
Yeah.
I don't, yeah, he actually proves that if you have a group which contains a copy of the integer of the subgroup, that has an infinite, an element of infinite order, then any two to really fit which have the same standard entropy are isomorphic. And the proof is like just 2 lines long, because we just have, well, you have an isomorphism to the copy of the integer. Now we can just build a new isomorphism process by process. That's it. So it's actually very easy. And then I use a kind of measured equivalence relation version of this. So we get it for all groups with the caveat that you have to assume that the newly fixed alphabet is using at least 3 symbols. 2 symbols didn't work because of it's got some weird technical thing and Brandon removed stuff. So now we know it's
yeah. So now, like, technically, the side I presented is possibly incomplete up to the issue of whether they're a non-countable sofic group. But yeah. So Brandon also has defined a different entropy theory for general countable groups that he calls the Rockland entropy. And for that one, interestingly, for non-sofic groups, we don't know that Bernoulli shifts have the right entropy. But yeah. Yeah. Mhm. Yeah, I think so. I mean, I've had like brief conversations with like Tim and Liz about that. Yeah, probably for other graph sequences that convert to something that's not a Cayley group or a Cayley graph, but something that's maybe nice enough, you can probably do similar things. Killer factor. So what would a factor map be between systems? So if there's no like symmetry group built in, I guess.
you can still be happy. And then you can think of your process as an extension, and maybe you have 2 extensions that have the same base. Then I think extension after relative to the base. Yeah, I have a paper that's on viewboard, the perfect entropy theory for viewboard.
Yeah. Sort of, yeah. I'm hesitant to use the statistical physics language because it might be saying something that's not exactly what you mean. But yeah, I can maybe show just the one. See how many extra slides I had. I obviously wasn't going to need these. Let's see. maybe a question related to what you're kind of close enough anyway. You can ask like if you have this sofic entropy along like a random graph sequence, you can define that by taking an expression that maybe looks kind of familiar. You can ask like, oh, is that like a typical sofic entropy? And there's conditions where you can say like, yes, that is a typical sofic entropy value. And then this you can actually calculate in some cases, like David Cameron was showing. That's the first moment thing you can calculate. So there's conditions for when like you can do the second moment method thing, and then like this first moment, like annealed entropy actually gives you the sofic entropy value. Yeah, and actually I have some work showing that that's always true if you have like a tail triviality or non-reconstruction under assumptions on the interaction, which I would maybe like to get rid of, but yeah.
Entropy theory, you can also define structure. And so then structure is like the sofic structure is the limit of what so it's sofic entropy minus minus the so you have a variation.